Good afternoon, professors. I'm Kwai from Kiangsu Chekiang College, Kwai, Chung, and our topic is on the solution of the exponential Diophantine equation. P to the power x minus q to the power y is equal to ez squared. And there are 4 parts in my presentation. First, we found that in 2020, Bridgeton studied the solution of the exponential Diophantine equation. The first one has a unique solution, and the second one has no solution. And we know the solvability of this equation is closely related to 1.1, but there exists a gap in his proof. Given we have these two consequences, he also considered the equation, which is the main equation of our report, has no solution if x is odd, but no information about even x. Here is our first main result. We first suppose that p and q are distinct or prime satisfying the consequences. Then 1.2 has at most one solution in all positive x, y, z. Next, we study the number of solutions to 1.3, where p satisfies this range of x. In theorem 1.2, part A, 1.3 has at most one solution. If the solution exists, x must be even. Part B, 1.4 with exact value with p and q has a unique solution. Part C, we suppose this is the unique solution to 1.3. Then we'll have y is 2m if and only if m is 2 to the power k, p is a half generalized Fermat prime, and x is 2. Before proving our main result, I would like to introduce 7 lemmas. Lemma 2.1 has this inequality, and lemma 2.2 says that if x is even, then we will have 2.2 where p and q are satisfying 1.2. And lemma 2.3 says that 2.4 has no solution. And lemma 2.4 to 2.6 are some well-known results on the possible range of the solution to 2.5. And lemma 2.7 collects some standard results from primitive Pythagorean triples. Now, I would like to talk about the main ideas of theorem 1.1's proof. We first suppose p and q satisfy this range, and then let this be the solution to 1.2. If x1 is odd, we will have this contradiction. Therefore, x1 must be even. Then we can apply lemma 2.2 to get 3.1, and we claim this is the unique solution to 1.2. Step 2, we let this be another set of solution to 1.2. Then we can rewrite 3.1 and 3.2 as 3.4 and 3.4. 3.3 to 3.4. And step 3, we prove A is odd and B is 0. By combining the equation, we can yell that p to the power n2 minus n1 have this form. Since A is odd, we can write down these binomial coefficient expressions. And the equations give A is congruent to 0 mole p. That means A is a multiple of p. Let Pn be the highest power defining A. Then we will prove these congruences. And step 4, the congruences is divided into 3 cases. For case 1, k is 0, case 2, k is not 0, and k is divisible by p. Case 3, k is not 0, and k is not divisible by p. In the first 2 cases, we can apply this fact and get the formula 3.12. That means ACK is divisible by p to the power n minus r. And these 2 numbers are coprime. Then we can conclude these 3 results. And the last case, it is proven that ACK is divisible by p to the power n, and we can have this inequality. And from step 5, from the claim 3.11 and the expression, we can derive into 3.15 for some integer n3. n3 must be negative, and we can get 3.16. The assumption and the expressions implies this inequality, and we can conclude that A is divisible by p to the power n2 minus n1. Then we try to let A be this form and rewrite 3.9 as 3.17 and apply lemma 2.1 with this number to get this inequality. And this implies that 3.17 is false. Then 1.2 has at most one solution. In the scattered proof of theorem 1.2a, we suppose this is the solution to 1.3. Let x be odd, and then p to the power x have these consequences by the assumption. And the differences of this is either digit 8 or 2. Its part is that to be even. By some simple calculation, we can show that it is impossible in this case. Then we let x is even, then we can apply lemma 2.2 to get 4.1, which is the exactly from 3.1. And the equation 4.1 has at most one solution in this case, and 1.3 has at most one solution too. And theorem 1.2b, we know that 13 is satisfied the hypothesis of part A, so we will have 1.4 has at most one solution. Since we have this equation, then 2 to 12 is the unique solution to 1.4. And the sketch of proof of theorem 1.2c, step 1. We let M and P be this form and X is 2. Then P is satisfied these consequences. And it is clear that 1.5 satisfies 1.3. That means Y is the power of 2. In step 2, we let Y is equal to 2M. Then we would like to prove this number have the required form. By part A, X is even, then we will have this equation. That means it formed a primitive Pythagorean triples. By lemma 2.7a, there are 4 cases as follows. For case 1, n is even, then m must be odd. We can write down 6.1. Using the similar ideas of proving lemma 2.2 and lemma 2.7c, we will have this result. And the facts give us p to the power n is divisible by 13. We can yell that p is 13. We can get this equation from 6.4, but it contradicts lemma 2.3. In case 2, z is w squared, then mm must be odd, since the expression is still valid, so p is equal to 13. And we will have 6.5 holes only when this result exists. Therefore, L is 3 and k is 2. W squared is 12. We have a contradiction. And case 3, m is even, then m must be odd. By the similar analysis as case 1, we can see this. And let m and qk be this form, we can reduce 6.6 to 6.7. And we know that qk is a prime, then the expression 6.7 implies that p is equal to qk. First, in direct checking, we can check that these values have their required form. In case 4, none of them is a square, then mn must be odd. The unique solution only exists when p and z have this value, and we will have both xy is equal to 2, then we will have this 2 form. Well, this p is the correction to our report. And it's time for the alternative proof from 1.2b. We would like to prove that 2.4 has a unique solution. And lemma 2.3 implies that n is odd, then we will have 2 cases. Case 1, y is odd, then we can write down 2.4 as 5.1. And since it is not divisible by 3, so 5.1 does not hold in this case, and 2.4 does not hold too. In case 2, y is even, then we can suppose the general equations 5.2 has a solution. Then the case y is greater than x is impossible. Then we can put these values into 2.5 to obtain these 2 results. And this delta is the correction to our report. Now, lemma 2.4 says that all the integral solution of the equation 5.2 has satisfied this range of x. And we can rewrite 5.2 as this inequality. And the main ideas of the remaining proof, we use lemma 2.6 and the directionless approximation theorem types, with different sets of k and b. Then, we can conclude from the direct computation that 5.2 has no solution. To conclude, from 1.1 tells us we have this equation has at most one solution if p and q satisfy these consequences. And from 1.2 study the number of solutions to the equations, particularly the unique solution is related to the half generalized Fermat's prime. And 2 different proofs of the uniqueness of the solution of this equation are given. So it fills up the gap and bridges the proof. And we have the conjecture. The equation has at most one solution for all any odd primes p and q. This is the end of my presentation. Thank you.